Hi, I'm Tarek Alvi and this is my video for a counting circuit. In this video, I'll provide a working example of my counting circuit prototype in PCB, as well as an explanation of how the circuit works. So, here is a working example of my breadboard prototype. First, you connect the power, the segment display turns on, and you make it start counting by pressing the button, and you can also reverse the count using the slide switch. Following that, here is a working example of my fully soldered and encased counting circuit PCB. So you use the first slide switch to turn the display on, make it start counting by pressing the button, and reverse the count by flicking the other slide switch. The purpose of this counting circuit is to make the 7-segment display put out readable numbers that count up or down at a steady pace. One of the defining features of this circuit are the integrated circuit chips. But before I go through those, I'm going to talk a little bit about what makes the aforementioned steady pace work. I present to you the NAND gate oscillator. The steady pace of the counting relies on the clock signals that the NAND gate oscillator produces. Clock signals are a type of wavelength that only alternates between two singular states of low and high. Visually, these kind of look like boxes, which is why they're also called square waves. The clock signals are produced by the teamwork between two capacitors. One large 100 microfarad electrolytic capacitor, and one much smaller 0.1 microfarad disk capacitor. The larger capacitor controls how long the clock signal is put out for. It fully fills up with charge before sending that energy out into the rest of the circuit. However, there is a 1 mega ohm resistor immediately after it in the circuit, which means it will take a much longer time for all of the energy within the capacitor to drain out, leading to the clock signal being sent out longer. Meanwhile, the smaller capacitor controls how fast the rate of the clock signal is. This happens because one side is connected to the output of a NAND gate, and the other one connects to several components connected to the inputs of the NAND gate. The NAND gate works so that it will put out a high output at every combination of binary inputs except for two high inputs, in which case it will put out a low. The small capacitor will receive a high from this NAND gate since at least one of its inputs is low. This same path is also connected to both of the inputs of the next NAND gate, resulting in a low output to the rest of the circuit. However, once the small capacitor fills up to just above halfway, it begins discharging into the rest of the circuit, making it so that there is a low input in this area in between these two NAND gates. Now, both of these inputs are low, resulting in a high output from this NAND gate. This causes the clock signal to go from its low state to its high state. But when the capacitor discharges all of its contents, it begins filling up again, and the states of the inputs and outputs reset, causing the clock signal to go from its high state back to its low state again, and this happens repeatedly until the 100 microfarad capacitor fully discharges all of its contents. The next chip is the 4017 decade counter, which receives clock signals and counts the number of square waves at the steady rate that they come in, but can only count from 0 to 9, as indicated by the decade in its name. The information from the 4017 gets inputted into the 4510 BCD converter. This chip converts the signal that was previously expressed using 10 separate outputs into an output consisting of only 4 pins, each with its own assigned number: 1, 2, 4, and 8. At this point, the circuit is still counting up to or down from 10, but the way it's visually shown requires more mental math because it adds up the numbers assigned to the pins that are firing and counts up to 10 that way. It is worth noting that for my breadboard prototype I used a 4516 instead of a 4510, but they function in the exact same way. The only difference is that one counts up to 16 while the other does not. The last of the ICs in this circuit is the 4511 BCD decoder. Its sole purpose is to convert the signals that it's getting from the rest of the circuit and channel it through specific pins that can be connected to a 7-segment display. There are 7 pins on the decoder to attach to the 7 pins on the display that are connected to the 7 LEDs within the display. To prevent the LEDs inside the display from popping, the pins of the 511 and the 7-segment display need to be connected using 470 ohm resistors. As you can see on the breadboard, it's pretty messy, but on the final PCB, that organization problem is solved with the help of resistor networks, which contains 4 isolated 1K ohm resistors in each. Thanks for watching.